All right, I wanted to come back to this theorem, basically finding an inflection point. We talked about this at the end of the period yesterday, and I just wanted to make sure we were clear on what this is saying, because I think when I was explaining it, I was thinking more in the terms of like rational functions, where this second derivative wouldn't exist at c, because in the original function there could be a problem. You know, like if you started out with something like 1 over x, just looking at the simplest form of that, you know, if we have 1 over x, you have an undefined there, vertical asymptote at 0, so when you take the second derivative, you also have that. But that's not always the case for every function, and I added an example. So we'll talk about two examples where this maybe will clear up what this is talking about. So your points of inflection can be where your second derivative is 0 or the second derivative does not exist. If the second derivative doesn't exist because of a vertical asymptote that was in the original function, then that's not a point of inflection. You know, the concavity can still change around that vertical asymptote, but a point of inflection is a point that actually lies on the graph. So, you know, a vertical asymptote isn't a point that lies on the graph, but we could have a vertical asymptote that shows up in the second derivative, and that's kind of what this is saying. And I added an example in here to explain that. So you can have a function that doesn't have a vertical asymptote in the first derivative, or in the original function, or maybe even in the first derivative, but in the second derivative it shows up. And, you know, so that point would still exist on the original function, but it's not, you know, the second derivative doesn't exist. And that would still be a point of inflection as long as the concavity changes around that point. Okay, so I did, like I said, I added an example hopefully to clear that up. So we went through this problem here yesterday, so I'm not going to talk about that one again. I'll just jump into the next one here. So first of all, we need to find the first derivative, so f prime of x, negative 15x to the fourth, plus 15x squared, and then we need to go ahead and find the second derivative. So negative 60x to the third, plus 30x. All right, so set this equal to 0. I'm going to factor there in my first step, actually. So let's take out a negative 30x, and then we're left with x squared minus 2x squared, 2x squared minus 1. Excuse me. So set this equal to 0. So this one right here, we have a 0 at x equals 0. And then this one over here would give us two zeros at x equals plus or minus square root of 1/2. Okay, you can write that multiple ways. Square root of 1/2 like this. 1 over square root of 2, square root of 2 over 2. It doesn't really matter. Take your pick. All right, so now we're ready for our table. Okay, keep in mind what we're looking for here. Points of inflection and the concavity. So let's go ahead now and make up our table. So we have x values around negative square root of 1/2. So we need something less than that. So I'm going to use, like, I don't know, use something that's definitely to the left. This gave us a 0. Something between there and 0. We may need to look at our calculator and see what exactly is the square root of 1/2. You know, so we can get some decimal approximation there. So square root of 1/2 gives us 0.7 approximately. So we need something between 0.7 and 0, so let's just say negative 0.5 or negative 1/2 and 1/2. Or you could use 0.5, whatever, it doesn't matter. So these are zeros here. Okay, so we're looking at our second derivative. And again, all we care about is whether or not this is positive or negative. We don't really care about the numbers, so let's see what we get here. So if we plug in -5 here, it's going to be a positive. And if we plug in -5 here, it's positive, so that overall is positive. Now if we plug in -1/2, right here is positive. Okay, but right here we end up getting a 1/2 squared is 1/4, times 2 is 1/2 minus 1 is negative. So we get positive times negative is negative. And then look at 1/2, we get the same thing in here. This is negative, but now it's also negative out here, so that's a positive. I'm missing a spot on my table here. And we need a number bigger than this, so pick a number bigger. And we get negative times a positive, which gives us negative, okay? So we have points of inflection because the concavity is changing, negative, positive to negative, and then negative to positive, and then back to positive and negative. So our points of inflection, one of them would be the negative square root of 1/2, and then whatever we plug in there. One is at 0, and then the other one is at positive square root of 1/2. Okay, so come back to your original function here, and these are going to be some messy decimals, but anyway, we got to plug those in. So -3 times the square root of 1/2 raised to the 5th power plus 5. Oops. So negative, I got a negative 5.8, oops. Negative 5.834. For that one. When we plug in 0, we're going to get 0. And then if we plug in, oh, that was supposed to, I'm sorry, that was for this one down here. Negative 5.834. So let me come back up here, fill in my negatives. Okay. So we get there 11.137. Sorry. Okay, as long as I got that in my calculator correctly. So I'm using a different calculator, so hopefully I have those correct. So anyway, this is what we get here for these points of inflection. Now, for our concavity, so we're just looking at concave up, wherever this is positive, so negative infinity up to negative square root of 1/2, and also between 0 and positive 1 square root of 1/2. And then concave down everywhere else. So negative square root of 1/2. That kind of looks like it's just over the 1. There we go. Up to 0. And then what was the last one? Square root of 1/2. To infinity. All right, so there we go. That's what we should get there. And again, check your points of inflection. Make sure that that is what you get there when you plug that in, because I'm using one of these other calculators and not a graphing calculator, so I can't look at the whole thing. So anyway, let's go on to the next one here. So this one, like I said, was one that we had done in the beginning part of the notes yesterday. So we already have this derivative. The first derivative is this, and the second derivative is this. So we know that there is no spot where the numerator is 0. But we do have 2 points where the second derivative, there's two c values, or x values in this case, at negative 2 and 2. I don't know why there's a dot there. Negative 2 and 2, where the second derivative does not exist. Okay, this is where our second derivative does not exist, right? So if your second derivative doesn't exist, then we have to look at, okay, are these actually points of inflection, or are they something else? So because these are two values that made the second derivative undefined, we go back and look at the original function, and since they are values that also make the original function undefined, these are not points of inflections, and we know that they're vertical asymptotes. Okay, so this graph, even though it does change concavity around the vertical asymptotes, it does not have any points of inflection, okay, because there are no points on the graph where the concavity changes. The concavity changes on the vertical asymptotes, or around the vertical asymptotes, so there are no points of inflection, okay, because again, the point has to be on the graph. The difference here is if we have something like this, okay, so let's say we do our first derivative and we say, all right, take my 5/3 out, inside stays the same, subtract 1 is 2/3, and then times the derivative of the inside is 2x. And then if I just kind of clean that up a little bit, 10/3 x times this other mess here, x squared minus 1 to the 2/3, right? There's no problems here, right? I could do this, I could find my increasing, decreasing, I can find my critical values and stuff like that. But I want to go to my second derivative to show you what I'm talking about here. So I'm going to use the product rule. So first, this is going to be my first function, and this is going to be my second function. Okay, so we're going to do first, so 10 over 3x times the derivative of the second. So that's basically kind of what we just did right there. So 2/3 times the inside. Minus 1 now is negative 1/3, right? So now we know we have a problem, right? Because this is being moved to the denominator. So the 1 and negative 1 that come out of here will be vertical asymptotes. Plus, the derivative of the first is 10/3 and times the second is x squared. Whoa, back up. Sorry, I forgot to do my chain rule here. Times the derivative of the inside. I was more worried about explaining the process to you here that I forgot to finish out the derivative. Times the derivative of the inside is 2x, sorry. Okay, so plus, now our second one, we do the derivative of the first is 10/3 times the second is x squared minus 1 raised to the 2/3. Okay, so when we clean this up, we're going to end up with 20x over 9, and then the cube root, try to squeeze that 3 in there, cube root of x squared minus 1, right, plus, no, wait, forgot about my second derivative that I had out there again. Okay, this right here is 20x, but we also have this out here, so 40, let's try that again, 40x squared, there we go. Now this one over here is just 10, and I mean you can write this as the cube root of all of that squared if you wanted to. That's really however you want to write that. You could also just leave it the way it looks right there. So I'll write it like this just to show you the other form, but you can just leave it in that form there, all over 3. Now, when we find a common denominator, I'm not going to finish this one out because I want to finish the other problem, but I just want to point out to you the difference here. So when we do this, our numerator would give us some zeros, and this is a messy function to try and find out your zeros. You're going to multiply by the cube root of this, which will actually, you're going to end up with a cube root being cubed, so that's going to take care of that. So you're going to have 40x squared plus 10x squared minus 10. so it actually isn't terrible. But your denominator here will end up giving you an undefined, okay? So your common denominator, basically, we're going to be multiplying this by 3 cube root of x squared minus 1 over the same thing, right? Because we have to get this denominator. We already have a 3, so we need another 3. And then the cube root of all this stuff. So when we do this, our common denominator will be this. So we can see we're going to have vertical asymptotes at 1 and negative 1. And then our numerator will end up being 40x squared plus 10x squared minus 10. So 50x squared minus 10. So you end up getting, the square root of 1/5. Which, or plus or minus the square root of 1/5. So those plus or minus square root of 1/5 would be zeros. And then the plus or minus 1 would be where the second derivative is undefined. So those would also be points of inflection, okay, what the values that come from this. But since those plus or minus 1s on this function right here are not undefined in the original function, right? There's nothing wrong with 1 and negative 1 in our original function. We can still count them as points of inflection, right? Because I can plug 1 and negative 1 in here. They're still going to give us zeros, but it's still possible for us to plug them into this function, into the original function to get the point, okay? So hopefully that makes sense to you, and if you want to, we can finish this one out later on. Just let me know. I can make another video like of me finishing that out. But I just wanted to explain that to you and show you the difference in those, because I think when I was explaining points of inflection yesterday in class, I was thinking more in the terms of when you're given a rational function to begin with. So let me finish this next problem here. My board keeps shutting off, so I think the battery's dying, so let me try and finish this last one here now. Okay, so for sine of x over 2, first of all, we need to take our first derivative, so f of x, f prime of x, sorry. So the derivative of the outside is cosine. So we have, cosine of x over 2. Oh, this is really bad. Try to move this around here. Let me fix this. Oh, what's going on with my board right now? Let me try it again, sorry. So cosine of the inside x over 2, and then times the derivative of the inside, right? We still have to do that. So the derivative of x over 2 is 1/2. And then second derivative, I'm going to move the 1/2 out front. The derivative of cosine is negative sine of the inside is, again, x over 2. And then multiply by the inside, which is the derivative of the inside, which is 1/2. So clean that up a little bit. We get 1/4, negative 1/4, sine of x over 2. All right, we want to know where is this equal to 0. All right, so we've got to figure out where is the sine function equal to 0. We're on the interval from 0 to 4 pi. Okay, so the first thing we're going to do is kind of think about, well, if I have negative 1/4 sine x over 2, we can kind of ignore the negative 1/4. Where is sine equal to 0? Okay, and like I said, the way that I do this is I kind of think of x over 2 as an angle, or as a variable itself to begin with, and I know that sine is 0 at 0 at 2 pi, I'm sorry, at pi, um, 2 pi And we can stop there because we're going to end up getting, when we multiply by 2, we're going to end up being out of our range here anyway. So to get x by itself, we get x equals 0 times 2 is 0, pi times 2 is 2 pi, 2 pi times 2 is 4 pi. Okay, so those would be your potential zeros, and then we have to go to our table to figure out whether they are actually zeros. So we need a number less than 0. On our graph, or on our interval, because 0 is at the very end, we can't really use anything to the left of that. So we're just going to have to start this out at 0, and then we'll have to go from here. So next. Let me fix this table. This is bothering me. All right, so we need a value that's going to be so here's our 0. We need a value between 0 and 2 pi, and then 2 pi and 4 pi. Well, actually, we could have 3 pi in here. Or no, never mind. So that would take 3 pi over 2, which is not a 0. So, okay, so let's just fill in some numbers here. So pi, 3 pi. All right, second derivative. So 0 gave us a 0, 2 pi gave us a 0, and 4 pi gave us a 0. So when we plug pi in here, again, we're going back to our function like this function here. We just want to know, is it positive or negative? So if I plug pi in here, pi over 2, sine of pi over 2 is 1 times negative 1/4 is negative. And then 3 pi over 2, sine of 3 pi over 2 is negative 1 times negative is positive. Okay? So what this means is that the 2 pi is our only point of inflection, because we don't know, because remember the concavity has to change from positive to negative or negative to positive, and because 0 was right at the end, we had a point of inflection that was right at the end of our graph. And the same thing out here, there was a point of inflection right at the end of this graph, but we can't say that those are points of inflection because we don't know if this was a negative or a positive out here. Same thing out here, they're not included in this. So the only thing we can say is that 2 pi is a point of inflection. So we have a point of inflection at 2 pi, and then I'm going to come back up to my original, which was just sine of pi over 2. So if I plug 2 in here, 2 pi over 2 is pi, sine of pi is 0. Okay? And then for concavity, we have concave up from 2 pi to 4 pi, and then concave down everywhere else in that table, which was 0 to 2 pi. Okay, so the last thing on these notes that I have for you is the second derivative test. Now, this is something that's covered, but one thing, and if you look at this bottom line, this is the reason why I don't like this. You can use it for if the second derivative is positive, we know it has a relative min. If it's negative, it has a relative max. But if it's equal to 0, then the test is inconclusive. It might have a relative min, it might have a relative max, or it might not have either. Again, my board's cutting out on me. So we don't really know. The test is inconclusive, and if this happens, we have to go back to the first derivative test. Both of these things come out of the first derivative test, so personally, unless you're directly asked to use the second derivative test, I don't really even use this one. I don't like it because sometimes it's inconclusive and we have to go back to the first derivative test anyway. But it is something that you're expected to know. They might ask you a question specifically about that. So anyway, there it is. But like I said, it's not really one that you'll see very often, if at all. and it's not really one that I use because the first derivative test is better. It gives you more information, and the first derivative test won't be inconclusive, where this one could be, and then you have to go back to the first derivative test anyway, so you might as well just use that. Okay, so that's everything. I'm going to send out some worksheets for you to work on today and tomorrow, and again, if you have any questions about any of those, you can just send me an email or a private comment, and I will do some of the problems in the video or something like that, and just send those out to you.